e to some power, e to power x. And in the end of last time, we've seen that this function is actually important for modern situations where you have a quantity with the property that its rate of change is proportional to the function itself. So let me remind you the important property of the exponential function. Reminder. Whenever you want to solve such an equation, that the derivative of a function or the rate of change of some quantity is proportional to the quantity itself, so it's some number r multiplied by the quantity itself. The answer is going to be e to the power r times x multiplied mainly by some constant. These are all the functions which satisfy such a relation, that the derivative is a number times the function itself. So in particular, these functions will going to differentiate e to the power rt, we get r times e to the power rt. And what's even more important, these functions are all the functions which satisfy this property. So, well, let's say a problem about this property. Simple problem. For example, population of bacteria, or at any time, the population of bacteria grows at a rate proportional to the size of the population. So this condition is usually true when the resources of growth are limited, when there is a limited amount of space and food. Typically, what controls the rate of change of the population is just the typical birth and death rates. And that's very typical assumption in these conditions. So we are given this assumption. And we are also given some data points. If at time equal to 0, the population is 10,000 and to make it really simple, t equal to 1, the population is, let's say, 25,000. What is the population at time t? So we are given two data points at t equal to 0. Well, I didn't say what units, maybe it's hours, days, what is affected, but that's not relevant. So when t is equal to 0, the population of bacteria happens to be 10,000, and when t is equal to 1, it happens to be 25,000. The question is, you want to know at any time t, what is the population? Well, let's solve this. Before I even start actually doing math, I want to give some convenient name to the quantity in question. So the quantity in question is population at time t. So that will be my notation. So population at time t. I'll denote it by p of t. Population Well, what do we know? We have three things here. One is this rate. At any time, population rate of change is proportional to the population size. How can I express this in terms of P? So what we are doing now is just translating the problem, we have a word problem, into mathematical terms. Here we started doing it by just giving a name to the function that we are interested in. That would be the population size at time t. And now I just want to go sentence by sentence and translate each sentence into mathematical terms. And the first sentence is important. The rate of change of population is proportional to the size of population. What does it mean in terms of P?
So it means that it probably, so P of t is probably P of t times E R t.
Okay, so that would be the conclusion from the mathematical statement. The statement itself is what's on the first line there. The rate of change of this quantity, which we know is E prime of t, that's the rate of change, is proportional to the size of population at time t. That's the population. Proportional means this is some number times that. Unfortunately, in this problem, we are not given what the number is. So for now, let's just say that this is some number r times P of t. That's all that's written in this first sentence. At any time t, so this holds for any t, the rate of change of the population is proportional to the population size. Next data point is at time t equal to 0, population is 10,000. How can I express it in mathematical terms? What does this sentence tell me about B? So let's start with this. Population is 10,000. Population, in mathematical terms, what is it? In terms of... Okay, how many of you are completely clueless about what happens with this problem? How many of you know what is the answer but are just... don't want to say it aloud? How many of you are awake? Okay, one, good. So please wake up and let's actually go with this problem. Once again, we have a population of bacteria. At any time t, we measure some number. This number, the number of bacteria in population, we give it a name, P of t. Next, I just want to go over this problem and translate every sentence into, well, in mathematical terms, as some statement about P of t. So we went over the first sentence over here, the rate of change of the population, which is P prime of t, derivative is the rate of change, is proportional, so it's some number times, to the size of population, which was P of t. That was translation of first sentence. I want to encode in some symbols the second sentence here. At time t equal to 0, the population size is 10,000. What should I write? Say it louder. Okay, what is plus 10,000? 10,000 is the initial size of the population. When we measure t equal to 0, so when we start the clock, we measure that the population is 10,000. How can I write it in terms of p? So something is 10,000. What is this something? P of 0, right? Tens. So it is the population size at time t equal to 0. Okay. Next data point. When time is 1, the population is 25,000. So once again, something is 25,000. What is this something? P of 1. And that's it. So, well, maybe the question is, what is P of t? Now we have a complete mathematical reformulation of this problem. As far as we are concerned, we can forget about this board altogether. The same information is written here. Exactly the same thing. Okay, next comes the mathematical solution. Hopefully it's not a complicated problem. Let's look. P prime of t is r times p of t. Well, we know how to solve this. We discussed it in the end of last class. Right here. So the population size at time t is a constant times e to the power rt. So that's the conclusion from the first line over there. I still don't know what c is and what r is. I now have two unknowns. But luckily I also have two equations. That's the second and the third line over there. So I'll use those. How can I use the first equation? The second line over there. P of 0 is 10,000. How can I use this equation to gain some information about c and r?
Yeah. Make a system of equations with p of 0 and p of 1, and then solve for r.
Okay, so let's do it. So what we should do is just plug in the 0 and 1 into this thing and compare the results to these numbers on the right, 10,000 and 25,000. The result will be a system of two equations and two unknowns, and hopefully we'll be able to solve it. So let's do it. P of 0 is c times e to the power r0. On the other hand, it is 10,000. Second equation would be c times e to the power r times 1 is 25,000. So now you have two equations about two unknowns. Okay. So now in our problem, once again, we started with this thing, now we have this thing. Again, these three lines encode the same information as the three lines over there. We didn't lose anything, but we simplified it a little bit. We now don't have any derivatives here. Finally, let's simplify these two things. So, how can I simplify this thing? What is e to the power r times 0? 1. Yes, so r times 0 is 0, e to the power 0 is 1. So first line tells you c is equal to 10,000. Second line, well, c is 10,000. E to the power r times 1 is e to the power r, and the result is 25,000. Okay, so e to the power r is 2.5. 25,000 divided by 10,000. What is r? Well, that's not such an easy question. It's some number such that once you raise e to this power, you get 2.5 exactly. E is, well, 2.7 something. What number should you, what power should you raise 2.718 to get 2.5? well, not an easy question. So what we do is we just give a name to the answer. And we call this name 1 of 2.5. This is called the natural logarithm. In a way, it doesn't solve the problem. We still have to find a way to actually compute what the natural logarithm of the number is. Well, we'll learn later in the course how to do it using Taylor expansion. Your calculators actually know how to find natural logarithms of different numbers. You have an actual button 1. But for now, let's explore what this natural logarithm is about. So let me explain what this thing is. So natural logarithm is the following thing. It's a way to solve a question of this kind. If you want to solve a question of the kind, so we are starting a new discussion, and discussion of what 1 is. E to the power y is some number x. So like this equation, by the way, we would have it not to answer a question with an answer. So here, let's have an answer. The answer would be population times t is 10,000 times e to the power 1 of 2.5 times r. 8 times
Times t.
times t. Thank you. Okay, so back to the general discussion about solving this equation. E to some power is x. So like it was in this question, the answer is, well, hard. So we can't really solve it using the functions that we already know. Polynomials, sines, cosines, square roots, whatever. So we give a name to the answer. We say that the answer is natural logarithm of x. So these two lines are just the same thing. E to some power is x. We call this power the natural logarithm of x. So the natural logarithm of x is the power to which you should raise e to get x. Let me use this word for collecting some properties of logarithm. So properties. Of line. Well, first property would be what I just said. The natural logarithm of a number is the power to which you should raise e to get this number. So if you raise e to this power, which is 1 of x, what is the answer? It's kind of logical tautology. It's almost obvious. So logarithm of x is the number, is the power to which you should raise the number e to get x. What happens if you raise e to this power? You get x, yes. So that's the first property, which is basically the same as just the definition of logarithm. Okay. Another thing, logarithm of 1. What is logarithm of 1? The way to think about this question is, what is the power to which I should raise e to get 1? That's the same question. 0. Okay. So here the reason was, so here will be the properties, here will be explanations. I can write just in brackets. E to the power 0 is 1. That's the same statement. Okay, so for other things, for other properties, I'll start with discussing an example, and then I'll write the general form of the property. So, suppose that somehow you found what is the natural logarithm of some numbers. Let's say natural logarithm of 2, you happen to know that it's about 0.69. So, suppose we know that 1 of 2 is 0.69 and some other digits afterwards, and 1 of 3 is 1.09 and some other digits afterwards. So I just tell you that this is true, or maybe you take your calculator, have 2, 1, and that's the answer that you see. First of all, what is the mean? The mean here is e raised to power 0.69 something is exactly 2. That's the mean of this phrase. The mean of that phrase is e raised to power 1.09 something is exactly 3. Which makes sense. E is about 2.71. So we should raise it just to a small to a power which is just slightly bigger than 1 to get 3, because 2.7 and 3 are really close. And you should raise it to a power which is smaller than 1 to get a number which is smaller than 2.7, which is 2. So it makes some sense. Okay, but next question is more interesting. What is 1 of 6? So this is the question, to which power you should raise e to get 6. Any ideas? So I want something like this. E raised to some power is 6. And the question is, what should I write here? Yeah. Okay, so kind of yes and no. So you try to guesstimate what power should be raised e to get 6. It's probably not 2 point something, just because, well, e to the power 2 is already, well, it's at least 2.5 squared, and 2.5 squared is 6.25, so that will be a little bit too much. But I want even more precise. I want to get the answer here with 2 digits of precision.
Find the rate of change.
Say again?
Find the rate of change, because we have 2 values, so find the rate of change between EPMs.
So rate of change would be about how fast the function grows at one particular point. So the rate of change of logarithm at point, say 2, would be what happens for values of x which are really, really close to 2. Rate of change here would be what happens about the values really close to 3. But here we really jump to a different value. Here we want to find 1 of 6. So probably a rate of change won't be helpful. Yeah?
I think it's the sum of.
Okay, the sum. I know that 6 is in fact 2 times 3. And I know that 2 is e to the power 0.69 something. I also know that 3 is e to the power 1.09 something. So what should I write here? Well, I know rule for how to multiply e to 1 power times e to some power. It's just e to the power of some, 0.69 plus 1.09. So that would be the logarithm. 1 of 6 is just the sum of these two values. 1 of 2 plus 1 of 3. Well, more generally, if I have logarithm of x times y, logarithm of a product of two numbers, the result is going to be 1 of x plus 1 of y.
I'm sorry, like,
Yeah.
I don't understand how 2 and 3 equal 6.
Oh, 2 times 3 is equal to 6?
Oh, 2 times, okay, I was thinking you're adding them. because-
Oh, no,
yeah.
that's, sorry. That's a small dot, that's not a plus sign.
Okay,
So it's the product of 2 and 3, and because it's a product here, the sum appears in the exponent there. It's not here, it's an exponent there. Because product of e to x and e to y is e to the power x plus y. And the corresponding property for logarithm would be that logarithm of a product is the sum of the two logarithms. Okay, let's, next question. Find what is 1 of 8. How to go about this? Yeah,
Would you just do, if you put 8, you can get 2 times 2 times 2 is equal to 8.
Right.
So it'd just be 0.69 times 3.
mm-hmm, yep. So 8 is just 2 times 2 times 2, or rather 2 cubed. So if I want to get the result, it's going to be 1 of 2 plus 1 of 2 plus 1 of 2, which is just 3 times 1 of 2. And if I know this, well, I'll find what it is. 0 times 3 times 0.69, something else, and then I'll compute what it is. Well, the general property. What is 1 of x to the power of y? How can I rewrite this? Y times 1 of x. Exactly like this here. 1 of 2 to the power 3 is just 1 of 2 taken 3 times. So it is 3 times 1 of 2. Here's the general property. Okay, let's discuss what is 1 of 1 half. How can I find 1 of 1 half? Given all we know so far. Yeah, exactly. So if I know that e raised to the power of 0.69 is 2, how can I get 1 half? Well, 1 half is just 1 divided by this thing, e to the power 0.69 something. I can write it as e raised to power minus 0.69. So this thing is just minus whatever logarithm of 2 is, or minus 0.69 something. And the general property will be logarithm of 1 over x is just minus logarithm of x. couple more. What is one of 3 halves? So 3 halves would be 3 divided by 2. Yeah.
ln of 3 minus ln of 2.
Okay, great. So 1 of 3 minus 1 of 2. What's the reason? Well, if I want to write 3 halves as e to some power, I can first write it as e to the power of 1.09, which was 1 of 3, divided by e to the power 0.69 something, which was 1 of 2. But then I can rewrite this as e to the power of the difference, minus 0.69 something. And then compute the answer, 0.4. So, if I want to find what number I should raise e to get 3 halves, well, it would be 1 of 3 minus 1 of 2. And more generally, logarithm of function x over y would be just 1 of x minus 1 of y. Okay. Let's go ask ourselves another question. What is ln of negative 2? What power should I raise e to get negative 2? How many times I should multiply e by itself to get negative 2? It's a kind of trick question. You can't. That's the right answer. So 1 of negative 2 is just not defined. Because what would it be? It would be some number such that e to this power is negative 2. So e to the power of, well, this number is going to be negative 2. This equation has no solutions. You cannot raise a positive number to some power and get a negative number. You can't multiply by itself a positive number any amount of times and suddenly get a negative number. So this thing has no solutions. And for the same reason, 1 of x is only defined for positive values of x. You cannot compute what is logarithm of a negative number, or you cannot compute what is logarithm of 0. No such thing. Okay, any other properties I want to discuss? Oh, maybe one additional property. What is 1 of e to the power x? I put it here because it's almost as simple as this property. So it's the number to which I should raise e to get e to the power x. What is this number?
Is it e to the x again?
Okay, almost. So,
1.
also close but not quite. So once again, it's the number, some number, such that once you raise e to this power, you get e to the power x. What is the number?
X?
X, yes. So if you raise e to the power x, you get e to the power x. Okay, so these properties you basically should remember and, well, be as fast in applying them as with just opening the brackets or expressing e to the power s plus y is e to the power x times e to the power y. So this should be just very basic skills which should become eventually just unconscious. We see Lama product, automatically you rewrite it as the sum of two logarithms. Sorry? Question? No. Oh, no. Okay. Just one warning, there is no formula for logarithm of a sum and no formula for logarithm of difference. Logarithm of sum is just what it is, logarithm of a sum. So there is no formula for 1 of x plus y. So careful with it. Okay, so let's do some exercise. Let's say I want to find the solution of this equation. 2 to the power x is 3. The equation is solved.
2 or 5?
Did you mean 2 or 5?
She said 2 to the...
Oh, 5 to the power x is equal to 3. Sorry. So let's say I want to solve this equation. 5 raised to some power is 3. How can I find this power? Well, before this we discussed the question of how to solve the equation e raised to some power is some number. With this thing, we can approach it slightly different. Now we know already quite a lot about logarithms. In particular, logarithms transform powers to just products. And that's very convenient because we know how to solve equations with products. Our problem was with an equation with powers. So solution would be like this. If this is equal to that, then logarithm of this is equal to logarithm of that. It's just if these two numbers are equal, then their logarithms are equal. But now is the fun part. Logarithm of 5 to the power x looks like a complicated expression. But thanks to this property, it's actually not. It's actually just x multiplied by 1 of 5. So how can I find x now? Just divide. Right. 1 of 3 divided by 1 of 5. Thanks. So please remember this trick. If you have an equation with, well, with powers, maybe on one side or both sides, it is a good idea in general to try to apply logarithms to both sides. Another example would be, if you have an equation of the form, I don't know, 2 to the power of x squared is equal to 3 to the power x plus 1. So any equation of this kind where you have on one or both sides expressions, maybe quite complicated expressions, which involve powers. So here I have 2 to the power x squared, here I have 3 to the power x plus 1. A good idea is to apply logarithm to both sides. It will simplify the equation immediately. So once again, if the equation is like this, apply to solve it, apply logarithm to both sides. Then use this property of logarithm. So it will be x squared multiplied by 1, 2 is equal to x plus 1 times 1, 3. And now it is basically a quadratic equation, something familiar. A number, 1 of 2 times x squared minus 1 of 3 times x minus 1 of 3 is equal to 0. That's a quadratic equation. Solve it using the formula for solutions of quadratic equation. X is 1, 3 plus minus square root 1, 3 squared minus 4 times this times this. Divided by 2 times this coefficient. So, and that would be the answer. So the idea, once again, is this equation is complicated. It involves powers on both sides. The trick is apply logarithm to both sides. If you have two quantities which are equal to each other, their logarithms are also equal to each other. And logarithms simplify powers because of this thing. They transform powers to just products. Once you have this simpler equation, solve it by whatever means you have. This particular equation happened to be quadratic, so I solved it using quadratic formula. If it was some other equation, well, I would apply some different means. Okay, so please questions about this thing. Yeah.
Should it be plus 4
Eh,
and
why
natural log of
possible,
3 is
yes.
negative.
So this comes with a minus sign, so it was plus. Thank you. So there is a correction here, it should be plus. Cancel. Other comments, questions, corrections? Yeah.
Okay, so I get the rules that drop this one for LM3, but how did you simplify it to the next slide?
So from here to here, I just brought everything to one side. I brought this x plus 1 times 1, 3 over to the left. Other questions? Okay, so next I want to discuss the behavior of this function 1 of x as a function of the parameter x. How does the graph of this function look like? What is the rate of change of this function going x? How fast does it grow? So let's start with the graph. So first observation. Logarithm of x is only defined for x which is positive. So I should not bother with any negative value of x. This whole part of the graph is going to be empty. Nothing. Next, well, let's just plug in some values. Let's say x equal to 1. What is logarithm? 0. So here I have 1 point. X equal to 1, y equal to 0. When is logarithm going to be 1? What is the number whose logarithm is 1? Okay, so let's discuss this small question. I want to find the number f such that 1 of x is 1. What is this number? E to the power. Okay, so what is the definition of 1 of x in some number y? It means that once you raise e to this power y, you get x. So what does it mean that 1 of some number is equal to 1? It means that if you raise e to the power 1, you get this number. So x is just e. Let's go back to this graph. 2, 3, and somewhere here is E. Here is 1. We get a point here. For what value of x the logarithm is going to be 2? One of what number is equal to 2? Think along similar lines. E squared, yes. So 1 of something being 2 means that once you raise e to the power 2, you get this number somewhere. So somewhere here, I know around 9.8, so quite far to the right, is going to be e squared. You'll get a third point at height 2. The next one is going to be at height 3 with x equal to e cubed, which is quite large. It's, I don't know, 20 something. So it will be off the board. Are there any other values, interesting values between 0 and 1 maybe? Let's see. When is the logarithm equal to minus 1? For what value of x the logarithm is going to be minus 1? Okay, so there are two separate statements. One is logarithm of minus 1 is indeed not defined, but I now ask the question like this. I want to find some number x such that logarithm of x is minus 1. Is there such a number? E to the negative 1. So the definition of ln of x being minus 1 is that if you raise e to power minus 1, you get x. And this is a number. It's just 1 over e. So somewhere here, a little bit smaller than 1/2, but larger than 1/3, is 1 over e. And you have this term. Then you have e to negative 2, so 1 over e squared, somewhere here, 1 over e squared, you'll get minus 2. And then you'll get smaller and smaller values with values -3, -4, and so on. It will be 1 over e cubed, 1 over e to the 4th, and so on. So overall, the shape is like this. The function logarithm is a function which at 1 is equal to 0. As you go to the right, it grows, but grows rather slowly. Just very, very slowly. As you approach 0, the function approaches negative infinity. It becomes larger and larger. Well, the value of logarithm becomes larger and larger negative number. Well, since we, just 1 second, on Monday we won't have a lecture, and the web work involves lots of problems about derivative of logarithm. We'll go over derivative of logarithm next time, but if you want to start your web work, I'll just give you the important hints. So derivative of logarithm of x is 1 over x. We'll go over this in more details on Wednesday. Okay, so thank you and have a great week. Please bring the assignments.